All right, section 6.3, energy as a state function. At the end of this, you'll be able to define a state function and apply the concept of a state function to predict energy changes in a reaction. Definition right off the bat. A state function describes the current state of a system and is independent of the path taken to achieve it. Internal energy is an example of a state function. So the height of an elevator is a state function. So here what we have is we're basically looking at a couple of different scenarios. So if we look at this as elevator A and elevator B, I'm going to write them out to the side. So elevator A and elevator B, their state, they are in the exact same position. Now, you can see that elevator A went from the ground floor to the 6th floor. It raised up, whereas elevator B started at the 10th, or started at the ground floor, went to the 10th floor, and then ended up at B. That's basically irrelevant. The path that they chose, or the path that they went to get to that stage 6 or level 6, does not really matter. So the height of an elevator is our state function. Okay. Now, a path function, the value of a path function depends on the path in which was taken, or the path which was taken. They depend on the sequence of steps taken between initial and final states. So work and heat are examples of path functions. Now, if we use that example of the elevator, well, there was one elevator that started at the bottom, went to 6. There's another one that started at the bottom, went to 10, went to 6. Now, those differences matter when it comes to discussing path functions. So an example, liquid ethanol at 25 degrees Celsius. So liquid ethanol has a very specific internal energy. So we're going to define that as U for internal energy sub liquid. Okay. The liquid ethanol could have been formed by melting solid ethanol or by condensing ethanol vapor. So gas to liquid or solid to liquid. In either case, the internal energy of the ethanol stayed the exact same because of the fact that internal energy is a state function. Now, however, the heat or work associated with the formation of the liquid ethanol is different for these two cases. So the heat, so I'll write that as the Q/W for this transition from gas to liquid, or the Q/W from the solid to the liquid. Those are going to be different. Now, ultimately, though, the internal energy is going to be a state function, so it's going to be the same. So here's our kind of illustration of that. So we've got our solid melting, going to our liquid, and our vapor condensing down into this 25 degrees centigrade liquid. Okay. Now, the question here was, is temperature a state function or a path function? Well, the answer is temperature describes the current state of a system and does not depend on the past history of that system. Therefore, temperature is a state function. So if you describe something as being 75 degrees Celsius or 75 degrees Fahrenheit, it doesn't matter if it came from 76 to get to 75 or if it came from 74 to get to 75. The state of it is 75 degrees Celsius. Now, a little bit of a review. A state function is a property of a system that depends only on the state of that system. State function is independent of the path taken to achieve that state. In contrast, the values of a path function or of path functions depend on the sequence of steps to achieve a particular state. So these two things do matter, but it's important to distinguish them from one another. State functions allow scientists to predict energy changes involved in reactions. Our internal energy is a state function, whereas heat and work are path functions. I hope this is helpful. This is something that we're going to be revisiting later on. We'll apply it and we'll talk about it in the application, or in those applications. All right, well, thank you very much. Have a good one.